Chapter 10. Genetic Engineering in the Biotech Century. Playing it smart or playing roulette with Mother Nature's designs.
All right, I started out our last session together by asking a few questions that led me to talk about two major issues in biology. One of the major issues I talked about was Mendel's experiments on the garden pea plant and his findings about how certain traits are passed from one generation to the next. The other major issue I talked about was the role heredity and genetics play in who we are, what we look like, and how we generally behave. And I need to stress that word generally when I say how we generally behave. Today, I'll be talking about the topic of genetic engineering. I'll be talking about what genetic engineering is, and I'll be touching on some of the potential advantages and some of the very real dangers that genetic engineering brings with it. I'll be giving some examples of genetic engineering projects, mainly in the field of agriculture, but also in the field of medicine. I'll also mention some of the cons of genetic engineering, especially the new microorganisms. And finally, I hope to finish up the lecture by explaining in more detail exactly how genetic engineering works. I hope to cover all these topics, but as you know, I sometimes get sidetracked or off topic in my lectures, and I sometimes run out of time, but let's see how things go. Okay, let me again start off with some questions. Do you realize that today we can grow orange plants or lemon plants from orange or lemon tissue in vesicles, which are small bladder-like bags? Some industry analysts believe that the day is not far off when orange juice will be grown, as it were, in vats, and there will be no need to plant orange or lemon orchards or groves to obtain orange juice. Question: is this a good idea and a benefit for humankind? Think about it. In the field of animal research, scientists are working to develop engineered super animals. These super animals will have enhanced characteristics for food production, such as extra nutritional value or lower fat content. Some scientists are also creating new kinds of animals, called transgenic animals, that can serve as chemical factories to produce drugs and medicines for other animals, and maybe one day for human beings. Researchers are also trying to create animals that can serve as organ donors for humans. The question: is this the right thing to do to animals? To make them grow to supersize or use them as organ donors for people? That's the question. All right. Here's another possibly more controversial question involving genetic screening in medicine. Should a couple expecting a baby be able to make sure through genetic screening that the child they're expecting does not show signs of having inherited some hereditary disorder, such as very poor eyesight or mental depression, or don't forget that tendency to be overweight? Another more personal question. If you could, would you use genetic screening to find out if your future child or grandchild had an inherited disease in his or her genetic makeup? Now, it's certainly true that many diseases and disorders that people get are caused by agents such as viruses and bacteria, or things in the environment, such as pollutants. But we are learning today that the cause of a number of diseases, like certain kinds of cancer, and a disease like cystic fibrosis, are in fact genetic. These diseases are thought to be passed down from generation to generation. Take the genetic disorder known as hemophilia, for example. Hemophilia is a genetic disorder involving the blood clotting factor. The symptoms of hemophilia are uncontrolled internal and external bleeding if the hemophiliac gets even a small injury. Today, thanks to advances in medicine, the symptoms of hemophilia can be controlled by giving the hemophiliac injections of the blood clotting factor that's missing from the blood. As far as the issue of medical screening for genetic diseases, do you know that in the United States today, hospitals are screening newborn babies for a wide range of congenital or hereditary diseases, such as hemophilia and cystic fibrosis? By the year 2004, every state in the United States was requiring that newborn infants be tested for a long list of inherited diseases. That's the good news. But And this is a pretty big but. With the knowledge we have of human genetics, and with the techniques we have for screening newborns, and even embryos, how long will it be before we're screening and maybe selecting human embryos for characteristics such as physical strength or other qualities such as eye or hair color? You name it. Should scientists engage in the genetic screening or engineering of human beings? But let me return to the topic of genetic engineering of plants and animals that's already going on in this biotech century of ours. We have already seen hints of the coming biotech revolution with the cloning of animals, such as the famous Dolly, who was born in 1996. By the way, did you know that Dolly the cloned sheep later gave birth to a lamb, demonstrating that clones originating in the laboratory are able to breed in the traditional way and are able to produce healthy offspring? Now just think about the implications of Dolly for a minute. Today, if we can produce cloned animals like sheep and mice, as we can, are we really that far from seeing the first human clone created? Some people will say, I can't wait for that to happen. Others will be horrified at the very thought. They believe that scientists who attempt to clone human beings, or animals for that matter, have overstepped the ethical boundaries of science and are even endangering the safety of humankind with their cloning experiments. Some people believe that genetic engineering and cloning is playing it smart. Others, however, think that genetic engineering and cloning is playing roulette with Mother Nature. Whatever you may think about the ethics of the genetic engineering of humans or animals, today biologists are using genetic engineering for two main purposes. One, in agriculture, to make hardier plants and crops for agriculture, and two, in medicine, to make newer and, they hope, better drugs for medicine. But let me start off with the field of agriculture. We can see the evidence of genetic engineering of crops sitting right on the supermarket shelves, probably in that box of cereal you bought at the supermarket recently. Did you know that by the year 2004, more than 50 crop plants had been genetically engineered, including potatoes, soybeans, and corn, just to name a few? Can you guess how much farm acreage is now devoted to genetically engineered crop production in the United States alone today? Well, let me tell you. Between the years 1998 to 2003, 68% of the soybean acreage, 26% of the corn acreage, and more than 69% of the cotton acreage were devoted to genetically engineered, or what they sometimes call transgenic crop production. That's a lot of genetic engineering going on in the early years of this coming biotech century, wouldn't you say? You know, I'll bet if you recently ate a tomato, it could have come from a transgenic tomato crop. And I'll also bet you didn't even know that you ate a genetically engineered tomato. For better or for worse, and in many countries, agriculture, especially but not only in the United States, has been impacted in serious and significant ways by the use of genetic engineering practices. The good news is that genetic engineering is able to produce crop plants that are more tolerant of stressful climate conditions, such as drought. In addition, genetic engineering can be used to control how fast or slow fruit ripens, so that crops can be shipped to markets far from the farm that grew the crop. Let me give you another example of one of the potential benefits of genetic engineering of crops. Plant geneticists have developed strains of crops that are resistant to some chewing insects, such as grasshoppers and beetles. The geneticists inserted a certain gene into the crop plants. This inserted gene makes a protein that injures the stomach of the insect that is chewing on the plant. Well, when that grasshopper or the beetle gets a bad stomachache from chewing on the genetically engineered plant, it decides to leave and look for another plant to eat. As a result, the good news is that crops that are resistant to certain insects do not need to be sprayed with pesticides that do tremendous harm to our environment when they get into our rivers and water sources. Now, for some bad news about genetic engineering. Let me tell you a frightening story about a gene-altered monster that almost got away. That is, it almost got out of the laboratory. In the early 1990s, a European genetic engineering company was preparing to field test and then commercialize on a major scale a genetically engineered soil bacteria called Klebsiella planticola. For your notes, that's spelled Klebsiella planticola. The genetically altered bacterium was developed to get rid of the crop residues, the part of the plant not harvested for food. The bacteria helped to decompose the plant material. The amazing and frightening thing was that the new soil bacteria, Klebsiella planticola, had been tested, as it turns out, in a careless and very unscientific manner by scientists working for the biotech industry. The biotech scientists believed that the bacterium was safe for the environment and would greatly aid farmers. Well, fortunately, a team of independent scientists decided to run their own tests on the gene-altered Klebsiella planticola. When they did, they discovered that the researchers from the biotech industry had apparently created a biological monster, a genetically engineered microorganism that could kill all terrestrial plants if it were released. After the exposure of the danger of this new bacterium, the gene-altered Klebsiella planticola was never commercialized. My point is that we need to be very careful about testing the safety of genetically engineered organisms before they come to the marketplace. In addition to finding evidence of genetic engineering in agriculture, we can also find evidence of genetic engineering in many of the drugs produced by pharmaceutical companies around the world. A key goal of genetic engineers is to make drugs that can cure genetic disorders such as cystic fibrosis and hemophilia, which I spoke about earlier. Another key goal is to produce new vaccines that will protect people against diseases such as smallpox and malaria, and against new diseases that will arise in the coming biotech century. Okay, I wanted to finish up the lecture by talking about how genetic engineering actually works, but I seem to have run out of time. So I'll ask you to read the section about how genetic engineering works in your textbook. It sums up in a nutshell how the process works. Well, that's about it for today. I'll see you next week.